Hello, my name is Steve Sims, and it's an honor to participate today in this memorial session for Rance. I knew Rance for more than 30 years, so his passing came as quite a terrible shock to me, as I know it was for many of you. In this talk, I'm going to tell you a little bit about Rance's leadership at Reactive Systems, which is a company that he co-founded with Scott Smolka and me in 1999. We founded the company with the goal of making formal verification commercially available for the development of embedded software. And this talk is based on a paper that Rance, Scott, David Hansel, and I wrote for the SPIN 2024 symposium that took place in Luxembourg in April, just a few weeks after Rance's passing a little bit earlier this year. It turned out to be one of the last papers Rance worked on, and for all of us, including Rance, I think it was a sort of a nice trip down memory lane to look back over the 25-year history of the company and see how far we've come over that period. So Reactive Systems, our company, is certainly one of Rance's legacies. So I'm very grateful to have the opportunity today to tell you a little bit about our company's journey. Okay. So I was fortunate to intersect with several different aspects of Rance's professional life. In 1991, I was a first-year grad student, and I took his class on formal verification, which is where I was introduced to the topic. Rance had a real gift for explaining very complicated subjects in a clear way that could be easily understood. Being in Rance's class drew me both to formal verification and to seeking Rance out as a mentor. And I was very grateful when Rance agreed to supervise my PhD research, and I got to work on formal verification research for him while I was in grad school. Of course, as was evident by Scott's introduction and the other talks here today, Rance's contributions to research in this field were both broad and quite impactful. And in this talk, I'll be focusing on Rance's work as an entrepreneur. So based on the research he was doing, he saw real potential for formal verification and to improve the way software is developed. So in 1999, we took the leap and founded Reactive Systems to try to make formal verification available in commercial software development processes. Okay, so to give you a little bit of a feel for the soil that the seeds of the company were planted in, let's just talk about some of the themes of the formal verification research that Rance worked on prior to starting the company. So what is formal verification? So we have a system and a specification, and we want to ask the question, does the system satisfy the specification? We want to formally define this check and preferably have tool support for performing the check in an automated fashion. So some of the themes that Rance investigated with regard to the formal verification problem are, what notation do we use for specifying the system behavior? He looked into process algebra such as Milner's CCS, or Calculus of Communicating Systems, Hoare's CSP, as well as different variants of these process algebras. He looked at graphical notations for specifying behavior in a more user-friendly fashion, perhaps based on finite state machines. He looked into different ways of giving the specification, perhaps as a temporal logic formula and doing model checking, or using the same notation that we use for the system. And then finally, once we have a system and a specification, how do we check for satisfaction? Model checking allows you to check if a system satisfies a particular temporal logic formula. Equivalence checking lets you check if two systems specified in the same notation behave equivalently. And pre-order checking lets you know if the system behavior is a subset of that specified by its specification. And then to tie all of these themes together, Rance worked on verification tools to put these different approaches into practice. Some of the tools he worked on were the concurrency workbench, which supported different process algebras. It supported model checking of mu calculus formulas, equivalence checking, pre-order checking. The process algebra compiler allowed you to give the syntax and semantics for a modeling notation, and it would generate a new front end for the concurrency workbench. So that would allow you to experiment with different types of notations for specifying your system. And then finally, the concurrency factory explored graphical notations for specifying system behavior, and it supported equivalence and model checking as well. Okay, so let's sort of go through a bird's eye view of the history of Reactive Systems Incorporated, and this will also sort of serve as an outline for the remainder of the presentation today. So as I said, we founded the company in 1999. We applied for and were awarded a Small Business Innovation Research Grant from the National Science Foundation that provided us with some seed money to start work on the company. One of the first things we undertook as a part of this SBIR project was a pilot project with Ford, which I'll be talking about a little bit more in the next slide. We released the first version of our product called Reactis for Simulink in 2002. By the end of the year, we had sold to 4 different companies, so we were happy about that. That's a good start. 2007, we opened a branch office in Japan and launched our second product, the Reactis for C plugin. 2010, we were finally awarded a patent for our test generation technique. We launched different version of Reactis for C in 2011. 2012, a product called Model Inspector. Fifth product called the Reactis for EML plugin in 2015. And we had obtained ISO 26262 certification for our products in 2021. And this is a standard which mandates a process for the development of safety critical automotive software. And we were certified by a company called TÜV Süd, who does certifications in that area. And to date, we've sold to a total of about exactly 179 different organizations around the world. Okay, so we had filed our incorporation papers and gotten some seed funding. One of the first things we wanted to do was look for a commercial partner that we could work with to undertake a pilot project where we would apply formal verification to some of their own software and see if this is really a feasible business opportunity. So we started attending some more industry-oriented conferences, and we met some engineers from Ford and talked to them about, what we wanted to do with the company. They caught their interest, so they agreed to work with us on a pilot project to basically analyze some of their software. And at about this time, many companies, including Ford, were starting to adopt Simulink, which is a modeling notation offered by MathWorks. Companies were starting to use Simulink to model their software. So Ford gave us a model of a powertrain application to analyze. It wasn't a huge model, but it wasn't a toy model either. It corresponded to about 1,000 lines of C code, consisted of both Boolean and integer variables, so it was infinite state. What we did was hand translate the Simulink model to the input notation of an invariant checker to check some properties of the model. We were able to find some dead code in the model and some violations of Ford's modeling guidelines. So this sort of piqued Ford's interest and gave us some hope that there would be a market for formal verification in the commercial development of embedded software. Probably the two key impacts on our company were that it pushed us in the direction of Simulink as the modeling notation, and it pushed us into the automotive industry as a potential domain for the use of our products. Okay, so Simulink is the modeling notation that we used in the Ford project. So what is Simulink? Well, it's actually 4 languages in one. It has 4 different components. The first is a graphical synchronous data flow language, an example of which is shown here. You have blocks that are drawn on the screen and then signals which connect the blocks. So each block has a set of input signals that it reads and then computes some output. In this case, it's computing the disjunction of its inputs. So in addition to logical operator blocks, there are relational operators, mathematical operations, and more complicated functionalities such as integrator blocks. Models can be hierarchically designed by breaking them down into subsystems, each of which has a set of inputs that it reads and outputs that it updates. State flow is a state machine notation, so you can insert a state flow diagram into a state Simulink model, and it sort of acts as a subsystem of the model. You can insert chunks of C code anywhere in the model to implement behavior. Then you can also insert MATLAB code, which is the matrix manipulation language of MathWorks. So I'll collectively refer to all of these parts as the Simulink model. Okay, so we now faced a major decision point in the direction we wanted to take with our tools. Do we use Simulink as the modeling notation that our tools support? Or do we come up with a homegrown language that we develop ourselves? As I mentioned previously, Rance and the other co-founders had done a lot of work in studying what makes a good system specification language for formal verification. So we thought we had a lot of good ideas about what that should look like. On the other hand, we'd seen that Ford is already using Simulink to some extent in their process, as were many other companies at that time. So it's a real decision, which way should we go? I think I've let the cat out of the bag in the history slide a couple of slides ago, and that the name of our product, Reactis for Simulink. So we decided to support Simulink. So why do we do that? Well, it's a lot easier to convince engineers to try your tool if they already have the models. So Ford already had Simulink models that they had created for their software. So rather than first having to create a model in our language and then performing the verification, we could simply provide the checks that perform verification on models that they already have. So that was one key point pushing us in the direction of Simulink. Second, we were just a startup at that time, and the companies we were working with didn't know, how long we'd be around. Most startups fail within a few years, so they are very hesitant to invest in creating models in a homegrown notation that's not yet established. So that would be another hurdle if we tried to create our own modeling notation. In the early 2000s, Simulink was already actually starting to take off and actually dominate as the modeling notation in automotive and aerospace industries. And another key point is that from the Simulink model, you could automatically generate C code using tools provided by the MathWorks or other companies. Then that C code is compiled to become the application that's actually deployed in the product. So by tying in with Simulink, we're tying into the tool chain that's used to produce the actual deployed executable. And so in 2001, with the second round of SBIR funding, we decided to pivot and use Simulink as our modeling notation as opposed to developing our own homegrown language. Okay, so we had decided that Simulink would be the modeling notation we support. So the next question was, what functionality should we offer in our tool to help our users verify their Simulink models? And again, we were faced with a bit of a pivot. So, and the reason for that pivot was that the models we were seeing were just too big for state-of-the-art formal verification techniques of the time to handle. And so just sort of as a practical matter, to get something to market before our funding ran out, we decided to scale back our goals a little bit and switch from proving that a system satisfies its specification to finding bugs. So in other words, finding instances where a system does not satisfy its specification. In other words, we don't prove the absence of a bug, but we want to find bugs when we can and report those back to the user. The first type of check we implemented was a sort of generic checks of Simulink models. So does a model contain any dead code? Are there any divide by zeros? Are there any out-of-bounds array indexing or numerical overflows? And if we do find these, report them back to the user. Another benefit, aside from scaling up to bigger models of this approach, was that the specification is implicit. The user doesn't have to formulate any kind of specification. The specification is that the model does not contain any of these types of errors. And so it's much easier for the user to perform. They don't have to come up with a temporal logic formula. They just click a button and then get back an answer if Reactis was able to find any bugs in their Simulink model. And the second type of functionality we would offer was basically automatic test suite generation. Given a Simulink model, generate a test suite that comprehensively exercises the model. Okay, so we want to automatically generate tests from a Simulink model. So what is a test for Reactis? So here we have a small Simulink model. It has a set of inputs that it reads and a couple of outputs that it updates. So a test for this model is just going to be a simulation run where at each simulation step we capture the inputs that we feed in and the outputs that the model responds with. So we feed in some inputs, capture those inputs in our test. The model responds by updating the outputs and we capture those as well. We then go on to the next step, feed in some inputs, capture some outputs, and keep going for however long we want our test to execute. So Reactis Tester, the test generation component of our tool, takes a Simulink model as input and then automatically generates a test suite as output. And that test suite is going to consist of a set of tests where each test is just a simulation run of the model, which is a sequence of steps where at each step we capture the inputs that have been fed in and the outputs that the model has computed. So we're automatically generating tests from a Simulink model. So what are our goals for the test suites we're generating and what can they be used for? So probably the most important goal is that we want the tests that we generate to exercise as much of the model's behavior as possible. So we want to maximize the level of coverage that we attain when we execute these tests. But at the same time, we don't want the tests to take a very long time to run, so we want to avoid redundant test steps when we can. So we want to both maximize coverage but also minimize the total overall number of steps in our test suite as much as we can. And finally, we want to store both the inputs and outputs in our tests so that it makes makes it easier to perform different types of tasks with the tests that we've generated. So what are some uses for these tests? So the first is that we can use them to detect runtime errors in our model. We mentioned the different types of generic checks we wanted to perform, such as divide by zero, bad array indexing, overflows. So we can detect this type of runtime error as we generate the test because we're doing a very comprehensive simulation of the model as we're generating the tests. Second, regression testing. Let's say you modify your model and you want to check to see if those modifications impact the externally visible behavior of your model. So what we can do is generate a test suite from the original version of the model, then run that test suite on the new version of the model, and any differences in the outputs will be flagged. Similarly, we can compare the behavior of C code against the behavior of the model to see if the C code is behaving as the model specifies it should. So again, we just generate a test suite from the Simulink model and then run those tests on the C code, comparing the outputs computed by the C code against those that were computed by the model and flagging any differences. So how do we measure how comprehensive our tests are? Reactis uses a collection of coverage metrics to do this. So these are going to give us a way to measure how comprehensive our tests are. So to give you as an example, let's look at a logical operator block. So to measure how comprehensively we've tested this block, we want to make sure that we've evaluated the block to both true and false. So that's called decision coverage. We want to make sure that each of the individual inputs to the block, which are called conditions, we want to make sure that each of those is evaluated to both true and false. And then finally, we want to make sure that each input to the block has independently affected the outcome of the decision. And this is called Modified Condition Decision Coverage, or MCDC, which is a metric that's mandated by the ISO 26262 Automotive Safety Standard, as well as the DO 178C Aerospace Standard. So those standards mandate that you test to this level in safety critical software. So Reactis uses these metrics and others to, on the one hand, guide the generation of the tests, and on the other, to measure how effective a collection of tests is. Okay, so how does Reactis generate the tests? Well, we use a technique that we call guided simulation. The way this works is that we first identify all the different coverage targets in a model. So we look through the model, for example, find the logical operator blocks and say for every logical operator block there's going to be some decision targets, condition targets, MCDC targets. So we identify all those targets. We then simulate the model, feeding in some inputs and having the model compute outputs. We capture those inputs and outputs to store them in our test. And then as we're doing this test construction, we track the level of coverage. So we say, has this decision block evaluated true? Has it evaluated false? And then the guided part of guided simulation is in the next step, we identify some coverage target in the model that has not yet been exercised, and we try to select inputs which will cause that target to be exercised. So if a logical operator is not yet evaluated to false, we try to pick inputs that will make that logical operator false. And we keep iterating until we get the level of coverage that we want. So the hardest part about guided simulation is picking the inputs. So how do we select inputs that cause uncovered targets to be exercised? So we have two main approaches that we use. The first is, when we use SMT solvers. We identify an uncovered target and then formulate an SMT constraint such that if we can solve that constraint, it gives us the input values that cause the target to be covered. We initially had our own homegrown solvers, but then in 2016 we switched over to using the Z3 solvers offered by Microsoft. If this works, this is obviously the best approach, but given how complicated Simulink is, remember it contains the data flow part, the state flow part, you can have C code, you can have embedded MATLAB, so it's a very complicated language, so we're not always able to formulate SMT constraints to pick our inputs. And when we're not able to, we fall back on option 2, which is random input value generation. So we take into account input constraints that the user might have given, such as an input being within a range rather than a full floating point double precision value. We also have a set of heuristics that we use to try to increase the probability of covering new targets. For example, if we have a state flow diagram, and we've covered state A, but not state B, then we want to, in order to cover state B through random search, we start our searches from state A. So that gives us a higher probability of, at some point, covering state B. Our first release of Reactis was in 2002. So far, we've been talking mostly about Reactis Tester, generating test suites from Simulink models. The second component of that first release was Reactis Simulator, a model execution environment. If Reactis Tester uncovers any errors, it's very helpful to be able to replay those tests that lead up to the errors to diagnose and debug the problem. So Reactis Simulator is a full sort of debugging environment for Simulink models. It allows you to execute tests that you've generated by Reactis, or do random simulation, or even interactively construct tests yourself by feeding in your own inputs. You can control the stepping through your simulation with these simple forward and reverse stepping controls. You can hover over any variable in your model to see its current value. Unexercised parts of the model are highlighted in red to alert you to those. You can set breakpoints. You can visualize data values since the start of a test with the scope. So in the 2003 release of Reactis, we included a third major component called Reactis Validator. And what this does is it allows you to formulate requirements that your Simulink model should satisfy, and then Reactis Validator will then go and perform a check, an automated search, to see if it can find any violations of those requirements. And if it finds a violation, it's going to return a test in your test suite that you can replay to see why that particular requirement is violated. Requirements can be formulated as assertions or user-defined targets. Assertions are expressions that should always be true. If they ever become false, then that means your requirement has failed. User-defined targets allow you to specify scenarios that you would like to test to make sure your requirement is properly stressed. The notation that Reactis supports for defining assertions and user-defined targets are C-like expressions or Simulink state flow observer diagrams. And the technique that's used to perform the check is guided simulation, the same approach we discuss for generating tests automatically. So it can find bugs, it can find any violations of the requirements, but it cannot prove the absence of bugs or prove that the requirements can never be violated. So in addition to the guided simulation approach for performing checks and generating tests, Reactis does include some basic static analysis, and this allows it to sometimes flag different coverage targets as being unreachable, and it also allows us to determine that an assertion is impossible to violate, in which case you get a green check mark. So to recap, in 1999, Rance, Scott, and I launched Reactive Systems with the goal of commercializing formal verification in the development of embedded software. We had a bit of a pivot along the way to testing-based tools that are inspired by formal verification. They can find bugs, but not necessarily prove the correctness of the software we're working with. They can find runtime errors. They can help with checking if C code conforms to the behavior of a model. They can also help with regression testing and checking if a model satisfies its requirements. Reactis is currently used by companies around the world, mostly in the automotive industry, some in aerospace. I'd like to thank the Concur organizers for including this memorial session for Rance, and thank you for your attention.